Now let's make some substitutions here, and let's try to figure out and come up with an equation that would allow us to calculate the entropy changes of solids and liquids. Now solids and liquids are pretty much incompressible, but if we were to replace du in the equation by cdt, the heat capacity times the change in temperature, and then note that as the solids and liquids change their energy and their entropy, really their volume doesn't change much at all, then really the second term will go away, and we could integrate really the left-hand side and just the first term on the right-hand side of the equation and say that the entropy change for a solid or liquid is simply the integral of the heat capacity divided by the temperature times the differential change in temperature. And we integrate that from one state to the next. And so since the heat capacity is pretty much constant, as long as the temperatures don't change too much, we can pull that outside of the integral and integrate 1 over TdT, which is just the natural logarithm of the temperatures in the two states. Now again, if you understand all this integration, you understand all the entropy, that's great. If you don't, here's what you need to know. If you got a solid or a liquid, to calculate an entropy change for that solid or liquid, all you really have to do is use the heat capacity as long as there's not too big of a temperature change between the two states. Okay, what does that mean? Well, let's talk about the entropy of the block of your car, right? You start up your car, what happens? Well, eventually the block warms up, you drive to wherever you're going, you shut it off. Does the entropy of the block change? Sure, yes, of course it changes, because think about it. The block is hot, right? And as it sits there, it's going to cool down slowly but surely. That cooling down represents a dispersion of the thermal energy, right? A spreading out, an entropy increase of the thermal energy. So since heat is flowing out of the block's entropy must drop. How would you calculate the entropy change of that block? Well, use the heat capacity and multiply it by the natural logarithm of the temperature in state 2, which is just the temperature outdoors, whatever it happens to be, divided by the initial temperature. And that would allow you to calculate the entropy change of 1 unit mass of that engine block. And so you could quantify how much entropy flowed out of the block in that process as it cooled down when you shut it off and you're at work or school or wherever you're going, maybe home. Okay. What about an isentropic process of a liquid such as a pump? What about a pump? Is there anything that's useful here? I mean, I just described calculating the change in entropy of something pretty boring. Who cares, right? Your engine block's going to sit there and cool down. Tell me something I didn't know, right? I could have guessed that the entropy of the block goes down because the temperature of the block goes down. So show me something useful. Well, here's something very useful. When I was in college between my degrees, my master's and my bachelor's, I worked for a small company in, I believe it was Crawfordsville, Indiana, called Banjo Corporation. They make a lot of products for agriculture primarily. They make pumps and valves and things like this. Very good products. There are a lot of hand valves. Some are electrically actuated. The pumps are fairly rugged. They make it out of glass-filled plastic, so it's very strong, very dimensionally stable, temperature resistant, all the good stuff you'd want. And I remember talking to one of the engineers there at the time, and he was doing some experiments. He had these huge tanks where he was pumping liquid from one tank to another to generate pump curves, for literature for their pump, so that if you're speccing out a pump, you can look at the pump curve and see if it will work for your application. And I began to think about it and realized, how would you compare two pumps? Because there were a lot of competitors. They always say that, imitation is the highest form of flattery. Well, there were a ton of Taiwanese manufacturers that basically bought Banjo valves, copied them down to the nth detail, even the shape of the handle without the Banjo label on them, and would make them out of just regular plastic rather than glass-filled plastic. And you'd end up with a product that was a lot cheaper, but was basically crap by comparison. They leaked like crazy. They just weren't dimensionally stable because they didn't have the glass fill. They didn't have very good quality control, so there was a lot of variation in the size of the parts. And it was a pump that looked like a Banjo pump, but it was junk, right? You knew you didn't want it because you knew that the Banjo pump was very high quality and would give you long service life and be very effective and not leak and all those sorts of things. But how would you compare the two? What if you say, well, forget all that, I just want to see which pump operates the best, which one is going to use less energy? Okay, well, you could do an experiment where you hook up two pumps between the same two reservoirs and measure how much energy each one draws to pump fluid from one to the other, right? You can keep track of that, and that'd be one way to do it. What if you didn't have the luxury of doing that? What if you wanted to compare two pumps and they were both operating, you could take some measurements, but you don't get to just set it up any way you want because these tanks are expensive and maybe you're just looking at someone else's pump and they don't really want you to change anything in the setup. What could you do? Well, let's think about it from an entropy standpoint. Ideally, you don't want any entropy to be generated, so the entropy of the incoming and exiting stream should be the same, right? So the entropy at state 1, where we have P1 equals 100 kilopascals, and the entropy at state 2, where P2 is 1 megapascal, should be identical. If that's the case, then you should have no entropy change, and so the you calculate that 0 equals average heat capacity times the natural logarithm of the temperature ratio. But it's not the heat capacity that's 0, it's the natural logarithm of the temperature ratio that's 0. How do you get the natural logarithm to return a 0? Well, you put a 1 into it. In other words, the temperature at the entrance and exit should be the same. So a very simple way to see whether or not a pump is any good is measure the temperature change across the pump. Now, you need fairly sensitive instrumentation to do this, but if you measure the average temperature change from entrance to exit, you could get a feel for how good the pump is, because think about it intuitively. If the pump has a lot of internal friction, the temperature of the liquid is going to go up a little bit as it goes through, right? Because that liquid is going to cool the pump as it moves through. So measuring the temperature rise across two separate pumps operating in the same environment would allow you, theoretically, to tell which pump is the most reversible and therefore the most efficient, you see. So this thing called entropy is actually very useful and at least conceptually explains things quite well.